And so at this point, we're going to say something like on packet. And we're going to give it the P. And we're going to give it... Actually, that's a good question. Why is there no way for me on this to get out? Right, data offset is the one. So P is the header. And then in addition, we want, where does the data start? Well, the data starts at 4 plus how far, the number of 32-bit words in the TCP header, right? So actually, that's not even true. So the IP header size is p.slice.len. Ooh, actually, this slice, that's even better. So the data starts at the IP header size plus the TCP header size, right? TCP header size is that last value. Actually, how about we don't overwrite these and say this is IP. This is the IP header. And this we can just inline just to make the code easier to read. That way here we can use iph.slice.len. iph.slice.len. This is going to give us a TCP header instead of just P. TCP header. TCP header. It should just say port. All right, so on packet, we're going to give it the IP header, the TCP header, and also the slice of the payload, which in our case is then buff from, let's give this a helpful name, data I, from data I to the rest of buff. Right? So from the point where the headers stop and the rest of the buffer is the contents of the packet. And that's sort of the end of what main has to do, right? There's going to have to be some way to like send responses, and who knows how that's going to work. There's going to be timers and stuff involved, but at sort of the heart of it, this is the way packets get into the TCP state. Okay, so now we need to actually implement that, right? So we're going to have to implement default for state. And we don't quite know what that looks like yet. We're also going to have to impl state and have something like a on packet that takes a an IP header, which is going to be what was it, ether parse IPv4 header, a TCP header, which is going to be an ether parse TCP. Oh, these are actually, this is IPv4 header slice. This is TCP header slice, and data, which is going to be just a bunch of bytes. And we don't really know what we're going to do in there, but for the time being, we're sort of just going to print this out. iph.sourceAddr, iph destination adder. Now we're gonna, I guess, just show the ports numbers directly in here. And so it's gonna be source adder, then TCP header, source port. And then the same but destination. And then finally, we're going to give data.len. This is mostly just to tidy up our interface, right? Oh, I probably did something stupid, didn't I? An inner attribute. Oh, I have messed up, don't I? This should not be that. And this should be pub. Well, crate, but whatever. They're the same. Actually, I also want my run script to... If compilation fails, I don't want it to run anything. What? Why does compiling... This makes no sense. Oh, that's not what I wanted. This is what I wanted. Great. All right, let's see. What else? No method on packet found. That's because this has to take mute self. Right, and the lifetime tick A here is the lifetime of the, basically of the packet itself. Which is basically the lifetime of this buffer, right? All right, so now this runs, and again, if we ping, nothing shows up because we're filtering those. If we try to connect to a given port, it's going to say, ooh, we got a bunch, ooh, that looks wrong. No, actually, that might be right. So this is saying that the body of that request is 1,440 bytes. That doesn't seem right. Oh, the data is until n bytes, of course. This also is n bytes. Because remember, when we fill up buff, we only actually, like buff is this long, but we only read this many bytes. So we should only be looking at that many bytes. So let's try that again. Now if we do this, 0 bytes, right? So the first packet we get is basically a header only packet. It contains no payload. Great, but this at least means that the math sort of worked out. So what this first packet is, in fact, if we, let's start this again. If we start our T-Shark and then do this, you'll notice that that message, if I can kill them again, is, and let's also kill this and also kill this. This packet that got sent is a SYN packet, and it has a bunch of like header fields. And so the question is, what do we do in response to that? Well, this is basically the first part of the TCP handshake. And there's a pretty decent description of that in, don't want this, don't want this, don't want this. These go away. This goes away. So this is when it starts to be time for the RFC. There's a operation, is that what they do it? There's a diagram somewhere in this document, but I can never remember where it is. I think it's down here, maybe. Arguably, I could just scroll through. Yeah, so this is the stuff that we no longer have to parse because etherparse does it for you. But where's the thing that shows the state? Oh yeah, there's a lot of stuff we're gonna have to get to here. Okay, so this is the diagram I'm thinking about. So this is the TCP connection state diagram. And so we're basically gonna have to implement all of these states. Initially, when you start out a new, so there are two states a socket can sort of, or a TCP connection can start out at. It can even start in the, here, I think they specify it further up too. Yeah, so there are a bunch of different states that a connection can be in. There are these states. And TCP here is sort of the TCP state. And so there is no connection currently. So that's what this closed here is. And so the idea here is that if you're closed, so if you're not expecting to get any connections, like there's no state for a given connection, then like even if someone tries to connect to you, you're not going to reply, right? If you're not listening on a given port, you're not going to reply. Whereas if you're in a listen state and someone tries to connect to you, then you are going to reply. So what we're doing here, actually, if you look at the code up here, this sort of on packet, here we're saying that if someone sends us a packet, if we haven't talked to them before, we're just always going to answer them, right? Or we're always going to deal with that packet. Now, that might not be the thing that we want to do. In particular, this means that basically every port is listening. And this might not be reasonable going down the line, but for now, let's just like stick with this. Like if someone tries to connect to us, we're just going to respond, yep, we're here. And so we're going to ignore this closed state and basically assume that every port is going to be listening. So if you notice at listen, there are a couple of different things we can do. We can either receive a SYN. You should read this as if this happens, then we do this. So if we receive a SYN, so as soon as this is the first part of the handshake, then what we send is an ACK, which is an acknowledgement of the SYN, and a SYN because we want to establish a connection the other way. So the handshake establishes a two-way connection in TCP. So this is the other person reaching out saying, hey, I want to talk to you. Do you want to talk to me? And this is saying, yes, I want to talk to you. Do you want to talk to me? At this point, we sort of note that we're in the state of we have received a SYN from the other side. And at this point, one of two things can happen. Either the connection can be closed, in which case we just like terminate the connection, or we receive a, or we receive an ACK of the SYN that we sent, in which case we don't send anything, but now the connection has been established. So this is sort of the initial TCP handshake. And so getting through the flow from here to here to here is basically how you do a server, right? So this is how you receive connections. On the other hand, if we wanted our library to establish a connection, it would start out enclosed, and then it would do an open, which creates the state for the connection, and then it sends a SYN, right? So this is sort of the opposite end of this receiving a SYN. Confession is fun. So if you're a client, you're going to go through this path of sending a SYN to the server and then being in the state SYN sent. At that point, hopefully, you're going to... So if you receive a SYN from the server, it means the server was trying to connect to you at the same time, in which case you can just ACK and then everything proceeds as normal. But in the common case, you send a SYN and you receive a SYN ACK. This is the SYN ACK that the server sent here. At that point, you're going to send an ACK to the server saying, yes, I do indeed want to talk to you, at which point the connection is established. You might wonder why you need this like two-way acknowledgement, and there are many reasons for that. The primary one is to make sure that the hosts are actually talking to one another, that there's not sort of some other host in between that's trying to do weird things. We're not going to get too much into the weeds of exactly why the protocol works the way we are. We're sort of going to naively implement this as if it were the, 1981. Sound good? We're going to assume that the internet is a safe place. And so, as you can see, there are sort of two different paths here for whether you're a server or a client. But as far as TCP is concerned, it doesn't really matter. All that matters is how you end up using that state. So I think what we're going to do is we're going to do the sort of TCP server part first, and then we can implement the client part later. The client part is what we're going to end up using for talking to other servers online. What happens if the final ACK from the client is dropped somewhere? So there are all sorts of ways for this protocol to be weird. Basically, there are a lot of timeouts in this protocol of things like you try to resend if you don't hear back. We'll get into all of that sort of dealing with retransmissions as we get later. But in general, TCP assumes that either you will receive an ACK eventually, or the connection is eventually going to time out and close, or it just stays open forever. Okay, so in this case, all we're doing is receiving a packet, And this diagram gives us a pretty good idea of what we probably want to do. Specifically, what we probably want to do is have this be an enum, right? We sort of want to encode the state diagram, and the default state is going to be closed. Now, this does mean that we're still going to sort of create an entry here for things that are closed, and we might want to sort of prune those. Like, there's no reason to keep this around if it's closed, but it's a good way to start to approximate the diagram. When we're closed, we're also going to be able to go into listen mode, and in fact, what we're going to do for the time being, so this is going to be state closed, but starting out, we're going to say that we're always going to listen on all ports. The other things we're going to need are SYN received. Let's, I guess, name these the same as in there. And we're also going to need established. And let's just like stick with those for now. There's a bunch of state we're going to have to keep for these two, but let's sort of start out in the very simple case of if we receive a packet, if it sort of depends what state we're in. So if we are in state closed, then all we're going to do is return. There's nothing more for us to do. If we're in state listen, then the only packets we expect to get in state listen is a packet that has a SYN set, right? That is the only thing we're expecting to get. And so if tcph.syn, so if the SYN bit is set, sorry, or the other way around, if SYN is not set, then I guess here we could do some logging and stuff, but here got unexpected SYN, only expected SYN packet. So in this case too, we just return. Right? Otherwise though, if we go down here, we got a SYN, and now we need to start establishing a connection. And so what that means is we're going to have to parse out the stuff from that SYN packet, and then we're going to have to send this SYN ACK. Okay, so we need to cook up a message that's going to be the response we send. And here too, like we're basically cooking up a TCP header. And so for that, we might as well just sort of reuse this, the ether parse, because they also have sort of the opposite of a TCP header. Now, here, it's a little awkward. This is going to need some way to send a message. So I think on packet, there's going to have to be some way for it to know how to send packets again. But let's just construct the packet in the first place. Okay, so we're going to have to create one of these. So we're going to send a SYN ACK. And in order to do that, we're going to have to set all of these. The question is, how can we create one? New. Great. So we're going to do new. And it's going to go in the opposite direction, right? So we received a SYN ACK from someone else, and now we need to respond to them. So when it says source port, that's going to be the destination port of the packet we received. Right? That's where we're sending from. The destination port is going to be the source port of the packet we received. The sequence number, we don't know yet. And the window size, we don't know yet. We'll have to figure out what those are. Then we're going to have to specifically... Again, we're going to read the RFC more closely, but specifically we're going to have to set SYN and set ACK, right? Because we're, SYN is going to be true and ACK is going to be true, right? So we're ACKing their SYN and we're also sending our own SYN. And then we're going to have to wrap that in an IP packet because we're sending it back to them, right? And so in order to do that, we're going to end up creating an IPv4 header. So it's going to be ether parse IPv4 header new. Payload len is going to be synac.slice.len. Time to live 64. Protocol. Ooh. It's going to be TCP. What else do we need? Source and destination. Okay, so the source is going to be the IPH dot destination, right? So we're responding. So we have to invert them. So if we're giving source, then that has to be destination address. And similarly, the destination is going to be the source address. Source header. And then ultimately, we're going to have to send these packets out. Ooh, that's a lot of things. Shouldn't be one for synac. Yeah, so there are a couple of questions in chat. The first one is, shouldn't it be 1? Oh yeah, these parameters are going to be set to something. They're not just going to be 0. I just haven't done it yet. And it is totally true that as you've already observed, right, we're keeping state for every connection. And so in theory, you can make the server do a lot of work with doing very little work yourself. And this is often known as a SYN flood attack. And it's something that modern kernels are actually pretty defended against, because what they'll do is they won't actually set up any state locally. They won't allocate any state locally until the connection is actually established. And so there are defenses against this. We're just not going to care about them right now because they complicate the implementation. So you're totally right that this is a problem in sort of real implementations. Okay, so we've constructed this packet. There's still some things we don't know, like what is this going to be? What is this going to be? And also, how are we going to write out this packet, right? Like there has to be some way for us to sort of send a reply here. Where this is going to get particularly tricky is when it comes to being able to send packets, like if there's a timeout, for example, that we're waiting for. And I don't have a good idea for how to do that. I think what we're going to do for the time being is just to give this guy a writer. Specifically, it's going to end up with something like an iFace. Now, of course, this is its own kind of stupid, because ultimately we're going to want to, for example, we're going to want to be able to send packets even if this is not active. But for now, we're just going to give it a mutable reference to the iFace, which we're going to call Nick. And what this means is that we can send packets ourselves, right? Just by writing out this Nick. Buff is going to be a 1500 U8. I guess 0 U8. Buff. Now, this is also not what is referred to as zero copy. Often you want the kernel to you don't want to not have to write things into memory more than once. We're going to ignore that as a concern. So this will not be highly performant, but it should be fine. So at this point, what we want to do is sort of write in the IP header, then the TCP header, and then any payload that we have. I guess here we're going to do something like let mute written is 0. So we're going to do ip.write. Ooh, what's the difference between write and write raw? I wonder. Interesting. I think write is what we want. What is it that implements write again for like things that are slices? For mutable references to U8. The writing updates the slice to point to the yet unwritten part. Yeah, so here we're going to have unwritten is going to be a mu to buff to the entire buff. And then we're going to write into unwritten. And then, and then we're also the synac is going to be written to unwritten. And the payload is going to be empty. And then at this point, we're going to write out the actual packet using send, right? So we're going to do nick.send, and that takes basically a buffer. And that buffer is going to be buff. Ooh, I don't know how that's going to work. It's going to have to be this, I think. Written is going to be let's see, how much have we rewritten? We've written well, unwritten is going to be this. And so we're going to write up until unwritten. Right? So this might seem a little weird, but out the headers. We construct the headers, then we write those headers into buff. And what this trick is going to do is basically we create a slice that points to the entire buffer. And every time a header gets written, the start of that buffer gets moved. And so this line down here is how much is remaining in that buffer, how much space is remaining. And however much space is remaining is how much we haven't written, right? Which means that the stuff we have written is everything up to that point, which is what this is doing. And I guess this means that on packet is going to have to return an IO result. I guess maybe usize. Unclear that it matters. And I guess we're going to have to use standard IO. Let's see whether this makes any sense. We're going to need prelude, probably. IO write is not implemented for U8. Wait, where is it saying that? Okay, there are a couple of issues. First, this expects a U8 of size 4, which is not what we're giving it. I guess this is going to have to be destination, and this is going to have to be source. It's probably still going to complain about that. Specifically, I wonder whether we're going to have to do like this, which is a little awkward, but maybe. And this is going to be source, source, source. Nothing found for IPv4 header. This we're going to have to use total len. All right, what else was it complaining about? This and also this. Now what is it complaining about? It's complaining in main about this. That's fine. It's now a question mark. It takes 4 parameters, but 3 were supplied. That's because we also need to give it now the network interface so that it can send additional things. Okay, what else do we have? Expected mutable reference. Oh, this should come first. You could use iter chunks to get that slice from destination and source. Is that true? Oh, because there's like a fixed size chunks thing now, huh? Chunks. Chunks exact, I think, is the one. But I don't know if it gives you that. I think it just gives you an iterator. Where's the implementation of... Implementation of iter. Yeah, it still gives you a slice. So it doesn't give you a U4, which is what we need. TCP line 29. Oh, this is okay 0. This is okay 0. No total len found for TCP header. It's because it's just header len is what we want. Because there's no payload. What else is it complaining about? The size for values of type U8 cannot be found. Maybe it's this. This we don't need. These we haven't done anything with yet, so they're unused. All right, so now we have something that's sort of running. And in theory, it's going to write back the appropriate ACK. So let's start up our T-Shark. And then let's try to connect on a port and see what happens. Well, something crashed. Not yet. Oh, it's because it's not terribly surprising. Okay, so we haven't actually figured out what we want to set these for. This is why unimplemented is nice. So when we try to create this, we need to set a sequence number, and we need to set a window size. And in order to understand what these are, we need to actually read the RFC. So the place to start for this is... where do we want to start for this? No. Nope. Here. Okay, so header format, that's fine. Here is where we're going to need to actually start reading and talk about what some of these fields mean. Just give me a second. I need to get some water. Okay, so let's look at what actually is in a TCP header. There's a source and destination port that we've already talked about, and there's a sequence number and an acknowledgement number, and there's a bunch of stuff down here. Let's talk about these two because they're relatively important for how the protocol works. And the protocol is pretty good at describing how they work. So the sequence number is the first data octet in this segment. So specifically, it is sort of the index in the data stream of the first data part of that segment. And you can sort of think of a SYN as a byte of its own. Right? So if SYN is present, the sequence number is the initial sequence number, which we're going to get back to, and the first data octet is one beyond that. So the SYN sort of counts as the first byte. And the acknowledgement number is the value of the next sequence number that the sender is expecting to receive. Right? So there's a diagram further down that makes this a little bit easier to follow. Where is it? Here. Yes. So this statement is basically entirely correct. In order to understand TCP, like you just need to understand sequence numbers and acknowledgement. There are a bunch of variables that need to be stored, and they're sort of stored almost no matter what state you're in. And so what we're going to probably have to do is basically have a struct TCB. So this is what they call the transmission control block. This is sort of the state that has to be kept for every connection. And a TCB is going to contain the fields that we give down here. And my guess is that we actually want, here's probably what we want, state. That's going to have to contain these fields. And in addition, it's going to contain something like, well, I sort of want to call it state, but let's make this connection. So instead of calling it the state, it's going to be connection. And this is going to hold a state. So this is the state that that connection is in. So this is going to be, for now, we're just keeping that. But let's look at what is in the TCP. Among them are things like socket numbers. We can ignore that. Precedence and security we can ignore for now. And then pointers to receive buffers we don't particularly care about yet. Retransmit queues in the current segment. This basically has to do with TCP is intended to provide reliable transports or reliable sends and receives across an unreliable connection. So the internet is prone to just like randomly dropping your packets or rearranging them, which means that sometimes TCP is told to like, hey, I never received that packet, and it needs to send them again, which means that TCP actually needs to keep a queue of things that it has tried to send in the past so that it can remember to send them again. And this is what's known as the TCP. This is what's known as the TCP retransmit queue. And so the way to sort of think about this is we're going to keep all the bytes that the user wants us to write, and then we're sort of going to remove them as needed. So we're sort of going to keep a buffer of everything we've tried to write. In addition, there are a bunch of variables that are related to the send and receive sequence numbers that are stored in the TCP. So there's a diagram down here that we're probably going to spend a bunch of time looking at, so it's useful to spend some time. The send sequence space is basically the bytes of data that we have sent. And there are a couple of points in that data stream. So send.una is what we have sent, but that has not been acknowledged. Send next is where we're going to send from the next time we send. Send.window is how much we're allowed to send. So TCP has this notion of, as a receiver, you can sort of limit how much your sender is allowed to send so that they don't overwhelm you with traffic. And so the how much we're allowed to send is the last point that was acknowledged plus the size of that window. So send.next can never go beyond, we can never send bytes beyond this boundary. Even though we might have them locally, we're not allowed to send them yet. And these are used for updating windows, which are going to change in all sorts of ways. There's also a notion of an initial sequence number. The initial sequence number is what we choose when we started the connection. That doesn't have to be 0. So basically, you can think of this as we don't have to name the very first byte as 1. Right? Like we don't have to start counting at 1 as long as both sides of the stream know what we call 0, right? And similarly, we keep similar sort of values for the receive buffer. Specifically, we keep track of what we are expecting to be the next byte we receive, and the window for receiving, and also the sequence number that the other side has counting as 0. Right? So this is why these segments are labeled. So everything that's in 1, so everything before this line, is data that has old sequence numbers that have been acknowledged. 2 is sequence numbers that we have sent, but that the other side has not yet said that they have. 3 is, so everything between here and here, is sequence numbers that we're allowed to use in some sense, right? Because this is the first bit of data we haven't sent. And we're allowed to send up to this much, right? Like a window more than where we got acknowledged. And so all of this we're allowed to send if the user gives us data. And 4 is stuff we're not yet allowed to send. And so 3 is referred to as the send window. This is where we're allowed to send. And the receive space is sort of similar in that everything before receive.next is stuff that we have received from the other side, and we're sort of done with that. We've passed it to the user space, hopefully, or we're about to, but there's like nothing. This is just data that we have received. 2 is sequence numbers that the other side is still allowed to send us. So it's within the window that we have announced to them. And 3 is stuff that they're not allowed to use those sequence numbers yet. And so we're going to have to keep all of this state for every connection. And so we might as well just sort of keep it already. So we're going to have a struct, which is going to be a send sequence. And that's going to have this, which I guess is going to be a usize. Next, which is going to be a usize. Window, which is going to be a usize. Urgent pointer, which I think is like a bool. I think the urgent pointer has even been like deprecated, so I think we can probably just ignore it, but let's keep it just in conformance with the spec. W1, in fact, let's also, just for our own sake, do this. I like it when documentation like keeps data, keeps comments from the protocol specs, because it makes it really easy to refer back and forth to them to someone trying to read the code and trying to understand it later. And in fact, for our own sake, so this is a usize, this is going to be a usize, and ISS is going to be a usize. And then in fact, this is probably useful to include as documentation on this struct. So this is something like state of the send sequence space. And then I guess we can also refer to 3.2. So this is RFC 793, section 3.2. And just for our own sanity, we probably don't need this to be like so. And this is figure 4. So this might help us later when we're like looking back at documentation things. In fact, these can arguably be proper documentation, so to speak. And similarly, we're going to have a receive sequence. Actually, we could maybe call this send sequence space. And this is the receive sequence space. And the receive sequence space is a little simpler. It's next, which is a usize, window, which is a usize, up, which is a bool, and IRS, which is a usize. And here too, we'll sort of keep the docs. One reason this is nice is because it means that we're going to have to switch back and forth a little less. At least one might hope. So this is the receive sequence space. So we'll do the same here. This is RFC 793, S32, figure 5. And similarly here, we don't need that. This can be this. And this will be this. Okay, so now we have those set up. And in addition, there are a bunch of variables that are used sort of as we discuss the protocol further down, that talk about segments, and we'll get back to that later. So the idea basically for us as sort of a TCP client is that we're going to make sure that, or we're going to want acknowledgements for these. So these are things that we have sent but have not been acknowledged. And if we have to send more data, we're going to use this space of sequence numbers. Right? So now the question becomes like, what are going to be defaults for these? Right? So a connection is certainly going to have a send sequence space and a receive sequence space. But we don't really know what's going to go in them. And so down here, I guess we have the diagram. And so this is where it goes into sort of discussion of the sequence numbers. And this is also something we sort of need to walk through. So every octet, so every byte of data that's been sent has a sequence number. And because we want to make sure that the receiver receives all of them in the right order, because every byte is sequenced, every one of them sort of can be and should be acknowledged. And the idea is that it's cumulative. So if I say, if I send you an ACK8, it means I have received all the bytes up to 8. And notice that it's not inclusive, right? So if I say, if I ACK8, it means everything up to but not including 8 has been received. The sort of the first numbered bytes. Numbering within a segment as the first data octet immediately following the header is the lowest numbered. Yeah, so if you receive a packet that has a bunch of bytes in them, then the first byte after the packet has the sequence number of that packet. So this is, when they talk about segment, a segment is basically just one packet. So this is the sequence number from the header of a packet that we received. And that gives the sequence number of the first byte of the data in that packet. And the sequence number space is finite, which is important to remember. So specifically, it's 32 bits long. And this means that like the sequence numbers are going to wrap around if you send enough data. Okay. In fact, In response to sending data, the TCP will receive acknowledgements. The following comparisons are needed to process the acknowledgements. Let's see. Yeah, so the idea is that we as a sender, we're going to send data to the other side, and it's going to send us ACKs back. And in order to do that, yeah, so this is going to be the last sequence number we have sent, but that has not been acknowledged, right? So this is the values from before. This is the acknowledgement field in the header when we get a packet from the other side. Acknowledgement from the received. Yeah, so this is the... So again, this is up to but not including, right? So they are expecting to get something with the sequence number next. And these are on segments, right? So these are headers of the current packet. So this is saying that the first byte of the current packet has the sequence number. And len is the number of bytes contained within this packet. And so necessarily if you add these two and subtract 1, that is the sequence number of the last byte in a packet. And so here they sort of define this notion of what an acceptable ACK is. And if you look at it, it's actually not that surprising, right? It's saying that if the... as long as the value they are acknowledging is one that we're expecting an acknowledgement from, right? So we believe we have not received an acknowledgement yet. We receive an acknowledgement, and that acknowledgement is something that we have actually sent, right? So next is what the sequence number we're gonna assign to the next byte we send, which means that if they try to ACK something that is greater than this, it means they're trying to ACK a byte we haven't sent. If they try to ACK something that is before this, it means that we've already received an acknowledgement for it, so we don't really care about it. And if you have a packet that's like on the retransmission queue, so something you might have to say again, you should consider it acknowledged if basically if the last byte, the sequence number of the last byte in that packet has been acknowledged. Yeah, so these sort of checks here are things we're going to have to add later. They're not important for the setup, but they are important to do. So we're going to end up having to look at these. I'm going to ignore them for now. So because the very first thing we have to do is the handshake, which is this part. Sorry. Yeah, so part of the problem is that TCP allows you to like establish many connections, right? So we have these quads, and there's nothing stopping you from like starting another connection with the same quad, but TCP sort of has to detect that this has happened. And the way it does that is by basically randomizing what you call the first byte of a stream. Because that means that because you randomize it every time, when you start randomly, you're unlikely to start on something that's valid for the other, for some connection the other side is still remembering from before, right? Like they're remembering this part of the sort of sequence number space. If you pick randomly, you're going to pick like somewhere out here because it's a very large space, and that is far outside their window. So they're just going to go, no, this is not a part of my stream. And they're sort of going to detect that something went wrong and probably terminate the connection. Specifically, they want to assure this even if TCP crashes and loses all knowledge of sequence numbers. And so this is why when you create a new connection, you choose a random initial sequence number. And imagine that it's just like actually random. In reality, they sort of want it to be not quite just random, but so that it increases over time to make it sort of maximally unlikely that you end up in the same sequence space as someone else. there's a bunch of assumptions here that they're unclear whether hold on the internet today. But we're just going to start with this being, I think actually random is probably what the current recommendation is, but it's not important. Yeah, so there's the initial send sequence number that's chosen by the sender and the initial receive sequence number, which is learned during connection establishment. So this is going to be, in our case, because we're first implementing the server, we're going to receive a sequence number from the other side. This is the sequence number of their SYN packet. So that is going to be where they're going to start transmitting, right? And in response, we have to send them a sequence number, which is the sequence number that we are going to start transmitting from. So at the beginning, the two TCP hosts are going to have to synchronize. And this is done in the sort of handshake protocol that uses SYN for synchronize, and that includes the initial sequence numbers. Right, so this is the actual handshake protocol. And so A tells B that they start at this, and then B responds, okay, I got your message, like I got your SYN, and then it sends I'm starting at this location, and A says, okay, I've heard that. And these two can be combined because they're both being sent from B to A, and that's how you end up with this handshake. Right, so this is the three-way handshake. So now that we have that, before we start digging into sort of actually sending data, let's try to now figure out how you're going to start a connection. I feel like these, we sort of want to be, we're going to have to figure out what to do about this on I don't think this can be default. But let's figure that out a little bit later. Let's not do this highlighting. So the question then becomes, what goes in this unimplemented part, right? So this is where we're writing a TCP header. We need to give the sequence number and the window size. Well, the sequence number, so because we're receiving a SYN and sending a SYN-ACK, right? So the sequence number we choose really just has to be random, right? We have to pick some number, which is where we're going to start transmitting from, and that number we have to give to the other side. So we're going to match on self.state, I guess. And 0 is random, so we're going to start at 0. Ultimately, we're going to change this value to be something that is actually random, the way the spec says. But for now, we're just going to say 0. This other thing is the window size, right? And this is how many bytes are we allowed to have outstanding. And if we look further down, quiet time, there's a lot of stuff in TCP. Yeah, where's there's like a suggested window size somewhere, but I don't remember. So the TCP spec is actually pretty easy to read if you sit down and read through it, and it is pretty interesting. They talk about a lot of different interesting challenges that can come up. Where's the place where it says window size? Window management suggestions. All right. Let's start with a window size of 10. Yeah. Seems fine. Again, like there are protocols that basically determine how you're supposed to set this. But for us, it doesn't really matter in this initial setup phase. This is more for us to understand what's going on. What we could do here is something like have a function that determines where to start. Now, the other thing is keep in mind that the other sites just sent us a SYN that we're acking, right? Which means that we need to acknowledge their SYN. And the way we're going to do that is by setting the acknowledgement number, right? And remember that the acknowledgement number is the next byte we are expecting to get from them, right? And so that's going to be, where's the sequence number? So